Welcome to Mastering Solutions. Let's draw a picture of what's happening in this question. So they tell us that we have one building here, second building here, and this is the alleyway. And they want us to figure out what is the angular width after the light comes out of here, or the radio waves. Because remember, radio waves are part of the electromagnetic spectrum. Usually we're used to thinking of visible light or ultraviolet light, but radio waves are part of that. So it's technically electromagnetic waves that are traveling at the speed of light. And so they want us to find the angle. And so we need to find what this whole width, that angle right there for the question. That's what they're asking for, right? Now, there's a few things that we need to think about to set this question up. First off, let's think about what equation are we going to use to solve for that. And we can use A times sine of theta is equal to P times lambda. And remember, P for single slit equations, because that's essentially what this is, right? The alley is acting as a single slit, and the cell phone hertz here, and the cell phone signal is acting as the wave, or the lambda, the wavelength. And so P is with a single slit, that is referring to the first order minima, not the bright spots like we were dealing with in diffraction gratings. And so if you think about this, P is going to give us this, or we can use this angle and P to find from this first order minima, wherever it is, let's say it's here, it'll give us this theta right there. But we need the whole theta, so we need to times this by 2, which will give us this whole unit because it will be mirrored. We have a minima here and a minima here. And now, of course, to get that, we'll have to rearrange the equation to solve for the theta here. And we can do that by dividing both sides of the equation by A, and then taking the inverse sine of both sides. Theta is equal to the inverse sine of P over A, P lambda over A, like that. So here's the final equation that we'll use to solve for the answer for the question, but the problem is we don't know all of these here. A, in this case, of course, is going to be the width of the two buildings. That's the slit spacing, right? And so A will be 15 meters. P is we're going to find the first order minima. And that's because we're finding the space. We want to find the width of the wave. So we're basically finding the width of the central bright max. And to do that, if we find the angle out to the first minima, well, by definition, the space between those two minima is the width of the wave. So that's why we're using P of 1. For this equation, for the single slit, the P can be whole integers starting at 1, 2, 3, etc. Now, what is the wavelength, right? We don't know that. Well, we can use another equation. And the equation that we're going to use goes back to the frequency is equal to the velocity over lambda. So if we rearrange this for lambda, we'll multiply both sides by lambda and then divide both sides by the frequency. So that will give us lambda is equal to the velocity over the frequency. Now the velocity, since this is a cell phone signal, as we talked about, it's an electromagnetic wave traveling at the speed of light. Really, it's lambda is equal to c, or the speed of light, over the frequency. We're given what the frequency is, 830 megahertz. And so we have all this, so we can solve for the wavelength here. So we have 3 times 10 to the 8 meters over 830 times 10 to the 6 hertz. And 10 to the 6 is for the mega. You can plug this straight into the equation up here for wavelength, or we could solve for it and then plug it in. Either way, just so we have it for our list, I'll solve for it. And you can plug in 3 times 10 to the 8th, or just to show you, you can also hit second and go down to constants. And number 1, speed of light right there. So we have c divided by 830 times 10 to the 6. And that gives us 0.361. Yeah, let's just say 0.361. That works. If you use 3 times 10 to the 8th and then divide that by the 830 times 10 to the 6th, you'll get a slightly different answer, very similar. It's just because of rounding error on the speed of light. So 0.3614, 0.361. If you use 0.361, it probably will get the same answer. I'm going to use a 0.3614 since that's what our book uses for the speed of light. So the wavelength in this case is 0.3614 meters. Okay, so now we have all the information. Now we can plug all this into our equation up here to solve for the theta. And theta is equal to the inverse sine. And P we said is 1 for the first order minima. The wavelength we found was 0.3614 meters. We'll divide that by A, which we said was a slit spacing of 15 meters. And so when we plug all this in, we get the inverse sine of 0.3614 divided by 15. And that gives us 1.38 for the theta. So 1.38 degrees. Now remember, that's from the center of the central max out to the first order minima. So we need to take 2 times theta to give us our answer. And so we have 1.38 times 2, and that's 2.76, which we could round to 2.8. So the width in degrees of our wavelength as it emerges from the two buildings in this single slit style problem is 2.8 degrees.